Okay, so let's move on and continue with this recap on probability, random variables, and models of distribution. Now that we have this refreshed knowledge about probability basics, I will approach random variables and also models of distribution of probability. Uh, Quick recap: we just approached these two main approaches on probability: the classic approach and also the frequentist approach that is the most used. So now we can assume that these sampling spaces can be sets of random events, and if we use elementary events as numbers, then we have a random variable. A random variable can be a function that associates each value of our variable to some probability, and this is very useful because we can create two functions for each random variable: the probability density function that associate each value of our variable with their corresponding probability. This is like a proportions of our variable, but approached from probability. And also we have discrete variables. This function can be called the probability mass function instead of density, and it's the typical function that we plot to see the shape of our variable. Also, we have the cumulative distribution function that pairs or associates each value of the variable with its corresponding probability, and also all of the other lower probabilities. Therefore, it's like the cumulative proportions to some point. Therefore, these two functions are the meat and potatoes of random variables, because they can be really useful to make some probability calculations. And also, as a curiosity, they are really interesting to understand how histograms are made. This visualization, I think, is very intuitive. So as you can see here, we can just create a discretization of a continuum that is uniform, the same width exactly, and we can just count the number of times an occurrence is in each bin. And therefore, we can calculate the probability mass, that is the relative frequency, in this case 1473, divided by 10,000, that is the relative frequency, or also called the probability mass. And therefore, if we divide that between the length, or excuse me, the width of the bin, then we have a number. If we plot all of these numbers, we create an histogram. So that's basically using a probability mass function to create a really useful tool to describe variables that are histograms. Okay, so these two functions also have properties. That one of them is the expected value, that is this abstract value that holds the highest probability of the density function, and can be easily calculated for discrete variables using sums, but can also be tougher to calculate when we have continuous variables, because we need to rely on integrals. We also have variance, that is this abstract number that reflects the dispersion of the density function, that also can be easily calculated using the expected value and squared values of the variable, but also with continuous variable can be tougher because we need integrals. Okay, so this is also the basis of the sampling distribution, so it's the basic foundation to make some inference, but we have to rely on theoretical models of distributions, specifically the sampling distributions, because in many times we cannot approach these two functions, the density or the cumulative distribution function, analytically, because maybe the integration is not possible, or we don't know the solution, or because it's very complex. Okay, so these typical theoretical examples are going to enumerate, so I will not delve into detail. For discrete variables, we have the uniform distribution, also the binomial distribution and multimodal distribution for discrete variables. That binomial distribution is for dichotomous variables, and also multinomial distribution is for polytomous variables, and the uniform is for any kind of discrete variable. And also for continuous variables, we have the rectangular, that is basically the uniform, but for continuous variables. We have the normal or Gaussian distribution, very used, and that it has a mean and standard deviation parameter. But also we have the student's t distribution. I like to call it the Gaussian t distribution, that has degrees of freedom parameter and is really useful, for example, for t-tests. We also have the Pearson's chi-square distribution, very useful distribution with some degrees of freedom too, and the Snedeker-Fisher's F distribution that has 2 parameters of degrees of freedom. This is like the standard thing to tell our undergraduate students on how to deal with statistical inference regarding distribution models. But also we have interesting distributions that are useful to implement. For example, when we have count variables, the Poisson distribution is very useful. And also regarding Bayesian inference, there are other stranger distributions that are very useful to make our operations. For example, the beta distribution is very useful in Bayesian inference and has 2 parameters, alpha and beta. And as you can see here, you can calculate the expected value and variance only using alpha and beta, which is very good. And also, as you can see here, the density functions can be widely different regarding its shape as you manipulate alpha and beta. So they can be very flexible as a distribution. We also have the beta binomial that is more or less the same idea as the beta distribution, but for binomial scenarios. We also have the Cauchy distribution that is very useful in Bayesian inference when we don't have a strong theoretical model to guide our decisions. And also have the gamma distribution and the inverse gamma distribution, very useful for correlations, and the inverse Wishart distribution that is kind of a strange distribution, difficult to tackle with, but very useful for covariance matrices. Okay, so that's it for now regarding distribution models.